Sophia, can you read to me the title? Lesson 5, what does it say? Nah, you read it wrong. Ronan won an award. Ronan, can you read to me the title? Lesson 5, what does it say? A little closer, but you're still reading it wrong. Still reading it wrong. Do you know what? Here's how you should read this. The law of conservation of energy. Thunder should rumble on the horizon. Lightning should flash across the sky. There should be a dramatic echo. This is one of the fundamental laws of the universe. This is my go-to law when someone comes up to me and says, "Hey, Kelvin, you're a physics teacher. Would it be possible to build a blah, blah, blah?" My answer is almost always no, and the reason is the law of conservation of energy. It's a fundamental law of the universe. A chill should be running down your spine right now. What does the law of conservation of energy say? Energy is neither created nor destroyed. It can only be transformed from one type to another. What this means is if you're looking at a closed system, a system that has no outside sources of energy, it's not plugged into an electrical outlet, or we're not adding gasoline, the total amount of energy that you start with has to equal the total amount of energy you end with. This is the law of conservation of energy. A more poetic way to say it, the amount of energy in the universe remains constant. We had some energy right after the Big Bang, and that amount of energy has not changed. We got a limited amount of energy to do stuff with. Both the kinetic energy and the potential energy of a block sliding down a ramp are shown below, only at the bottom position in the sketch. Fill in the missing values for the other positions. So here's what the law of conservation of energy says. The total energy has to remain constant. In your head, Allie, what is the total energy at the bottom? What's the total energy here? Same answer. What's the total energy here? Same answer, 75. What's the total energy here? Same answer. So how much PE at the top? And in this particular situation, all of the gravitational potential turned into kinetic at the bottom. Partway down, we still have 50 joules of potential energy. How much kinetic energy must we have? How much potential energy must we have? In words, the law of conservation of energy, I'll often abbreviate it as C of E, says the amount of energy a closed system has never changes. As an equation, stored energy initial plus motion energy initial has to equal the stored energy final and the motion energy final. But of course, we're not going to write it like that with symbols. We're going to write it as PE initial plus KE initial has to equal PE final plus KE final. Is that on your formula sheet? I don't know. It's my way of saying maybe you want to look and see if it's there, and if it is, you want to remember that it's there. Now, that's assuming we don't lose anything. If we want to be a little bit more accurate, we can include energy lost to heat. We can actually say potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. Oh, the numbers don't balance. Whatever's missing must have been lost to heat. And what I really mean by heat is all of the dissipative energies, heat and sound, etc. A skateboard park is a really good example of conservation of energy. Now, right now, I'm going to turn friction completely off, and I'm going to give this skateboarder potential energy. It's going to turn into kinetic energy at the bottom and then back into potential energy. Because I've turned friction off, this will keep going forever. So I'm going to give you some numbers. Here's a little pie chart, a little bar graph. What do you notice about the total energy in the system? It's remaining unchanged. That's the law of conservation of energy. Now, this is in a perfect world where we're not losing anything. This is in a 100% efficient system, which doesn't exist. Actually, it does in outer space. But if we add a little bit of friction, you'll notice the total energy is not changing. But as more and more energy gets lost to heat, the red bar, there's less and less energy left over for potential and kinetic. I stop going as high, I stop going as fast. This is a much more accurate skateboard simulation. What's the final result going to be? How fast will the skateboarder be moving? 0. How high will the skateboarder be? 0. This is the fate of the universe, by the way. The fate of the universe will be a few billion years from now. All of the energy will be evenly spread out all over the universe. And when you run the numbers, that means the average temperature will only be a few degrees above Kelvin. There will be no life in the universe. Spoiler alert, you're going to die someday, as will everything else in the universe. You're going to die someday. You know that, right? Death rate's still 1 to 1. No, babe, you're going to die. Just be aware of that. I also have a marble energy transfer device. What's a marble energy transfer device? A pile driver is another good example of turning potential energy into kinetic energy. This is the law of conservation of energy. It says energy has to come from somewhere, energy has to go somewhere. Got a couple of more little toys to show you, nice little examples. So, example 1, a projectile is launched straight up into the air. If its initial velocity was 75 meters per second, how high does it go? Now, we could solve this, don't write this down, we could solve this using kinematics. We could say VI equals 75, D, don't write this down, equals question mark, A equals negative 9.8, VF at the top equals, we could. We can also solve this with energy. We could start out by going KE initial, write this down, plus PE initial equals KE final plus PE final. Kinetic energy is the energy of motion. Is there ever a time where this projectile is stopped? Where? So you're saying the final kinetic energy is going to be 0? Yes, it will be. Potential energy, gravitational potential energy, is the energy due to your height. Is there ever a time when this has a height of 0, a potential energy of 0? Because we all know PEI is not a real province. Come on, they're a mayor, not a premier, right? They call themselves a premier, but we know better. They're a mayor. It's a town, not a province. And we get this, a half mv initial squared equals mgh final. Oh! Is there an m in everything on the left? Is there an m in everything on the right? Well, that's convenient. What am I trying to find? How would I get the h by itself? And I'll get this. The final height is equal to vi squared divided by 2g. Yes, you can put the 1 in front if you really want to for the 1/2, but Allie, can we just agree not to? A 1/2 is the same as a 2 on the bottom, right? And it's going to be 75 squared divided by 2 times, not negative 9.8, just 9.8. We're in Scalarville. and I get 287 meters. Now, again, probably if I wasn't told to use energy, I probably would have gone D equals question mark, VF is 0, VI is 75, A is negative 9.8, and then I would have said I'm going to use VF squared equals VI squared plus 2AD. I would have got the D by itself, VF squared minus VI squared all over 2A. I would have got 0 squared minus 75 squared all over 2 times negative 9. Wait a minute. That would vanish. What's a negative divided by a negative? Isn't that exactly what we ended up? Ha! We're doing a similar thing in a roundabout way, but where conservation of energy really shines is when I start looking at dissipative energies like heat, part B. Suppose the projectile only gets 125 meters high. How much energy was lost to air friction? Or, if you want to think about it a different way, how much work did air friction do in slowing down the object? This is the job for conservation of energy, G. It's going to be potential energy initial plus kinetic energy initial, or kinetic initial plus potential initial. Everything you start with has to equal everything you end with. Only this time it didn't, because I didn't get high enough. So there must have been some heat, energy lost to heat. I think we can still say, Adam, the same things are 0. Potential energy kinetic energy at the top is 0, and we're starting on the ground. Caden's going to put his phone completely away so it's not a temptation. Thank you. How will I get the heat by itself? Caden made my most irritating, sloppy mistake, and I'm glad he did, because this one drives me cray-cray, and kids do it all the time, and I don't know why, because to me, it's pretty obvious. There's a plus sign and a plus sign. How on earth would you say divide? And I don't know why. For some reason, on this specific equation, kids love to divide to get the heat by itself. I haven't figured out why. But it happens, and I know it's going to happen on the test this year with my 2 blocks. At least one kid's going to do it, and that's kind of the fingernails on the blackboard of my soul. Some equations I can understand where the mistake comes from. This one, I don't get it. There's no times anywhere, and they want to divide. Yep. It's teenagers. Caden, can I give you one piece of life advice? Don't waste any time trying to figure out teenagers. It cannot be done. Heat is going to be the initial kinetic minus the final potential. Heat is going to be a half m v initial squared minus mgh final. Do the m's cancel this time? Why not? No m in heat. Okay, so we're going to have to crunch this. The heat is going to be 0.5 times, what was m, 12? Times 75 squared minus 12 times 9.8 times 125. And I get 19,050. Double check me. I'll write down everything and then I'll round off to the sig figs. I'll go 19,050, which I guess to 3 sig figs would be 19,100 joules of heat. Prabner, what C want me to find? Yep. Yeah. Ah. Sorry? Yeah. That might work. I'd have to run the numbers. But one of the things you have tumbled on is I can certainly, because energy is a scalar, I can let the zero height be wherever I want, and I'll often move it around because, oh, I've got two potential energies at the same height. Why don't I make that zero and they'll both cancel, and that's less work for me to type. Okay? Yeah. Prab, what's C asking me to find? See, with our current skills, we would have a tough time doing this, but wait a minute. What did I find in part B? Looking for a word that starts with the letter H, and then has an E, and then has an A. What did I find in part? Heat. But another way to think about heat in this case is the work done by air friction. The work done by air friction. So you ready? I think we can say this. The work done by air friction equals air friction times distance. Hey, there's a force in this equation. Not MA, not winner minus loser, but I can figure it out from work. How would I get the friction force by itself? By, okay, I guess in this case, the average force, why am I saying the average force? Because air resistance, as you slow down or speed up, it changes. All we can handle right now is the average. Average force of air friction is going to be the work done by air friction divided by the distance. What was the work done by air friction? 19,050, also called heat. Over what distance? Were they in the same direction? Yes, they were. If you said, Mr. Dewick, could I call this negative because it's energy lost? I would be fine with that. This really didn't specify a specific reference frame. It just said find the average force. I'll call the force positive. So it's going to be answer button divided by 125, and I get 152 newtons. That's the average force of friction. Says Mr. Dewick has a very cool demonstration of conservation of energy. G. So you might have noticed as I teach, I always want to try and give you some kind of a trigger, some kind of a, hey, when do I use this? Is there a projectile? T-table. Are they talking about forces? This is a job for a? Okay. When do I use the law of conservation of energy? G. When you see that there is a change in height, a change in speed, and especially if there is a yucky, curvy path. Because if there's a yucky, curvy path, you would not want to use a vector-based approach that somehow had to take into account every change of angle of that path. You'd have to be doing the parallel perpendicular theta thing, every millionth of a millimeter. No. So really, when do I use this? Ski hills and roller coasters. This is fun physics. Example 2, at location Z, a 72 kilogram skier is traveling at 18 meters per second. How high up the next slope can the skier reach? Caleb, in this question, is there a change in height? Is there a change in speed? Is there a yucky, curvy path? This is a job for conservation of energy. Initial plus initial has to equal final plus final. Caleb, did this question want me to include friction and heat? Okay, otherwise if it said include plus heat, no. Are any of these zero? Now let's define what initial is. I think initial is going to be here, final is going to be there. Yes? Are any of these 0? Yeah? Of course PEI is 0. How they're a province, I don't know. Oh, at the top, for a split second, we're going to come to a stop. Okay. A half MVI squared equals MGH final. Oh, technically, did this question need to give me the mass of the skier? So if a little kid was holding hands onto this grown-up and they were both going at 18 meters per second, they would both get to the same height? In theory, yes. In real life, the grown-up would probably have way more air resistance and probably wouldn't get quite as high as the kid. But we're in our magic physics world where we ignore air resistance. I saw online, there's a physics teacher in the US who talks, he says that we live in the vacuum that we breathe. That's his phrase that he uses for kids. We're going to ignore air resistance. We're going to pretend we're in a vacuum, but we can still breathe. So we're in a vacuum that we can breathe in. That's what we'll do all our physics in. I kind of like that phrase. Example 3. Suppose it takes an average force of 245 newtons to pull the bow back a distance of 68 centimeters. How much work is done pulling back the bow? Well, I guess it's going to be 245 times 68. Oh, 0.68. Okay. And I get 166.6 joules. How much potential energy is stored in the bow? Say it again, Caden, you're right. So here's the mistake that drives me crazy. I see a lot of kids go, oh, potential energy is MGH. And they go, oh, he said 42 grams in part C and 9.8, and oh, that must be a height because it's got meters or centimeters next, and they do that. Are we changing the height here at all? Is this gravitational potential energy? So don't be plug and chug sloppy. We got to think this through. We have stored energy, but we stored it not by lifting, but by work. 166.6 joules. C, if the arrow has a mass of 42 grams, how fast should it leave the bow? How am I going to do this? Alessio, what's this question you want me to find? I don't think I can use a VI, a T. I mean, there is a D, but I don't have a VI or 0. I don't have a T. I don't have an A. You know what? This is a job for conservation of energy. Not because there's a change in height and there's a change in speed, but because we have work and energy being done. I think we can argue that all of the potential energy stored in the bow turns into what? So I modified the conservation of energy equation, Camille. I said everything we start with still equals everything we end with, but we're not starting with any kinetic and we're not ending with anything stored. Again, kids really want to put MGH here. No. 166.6, that equals mv squared over 2, or 0.5 mv squared, however you want to write that. What am I trying to find? Alessio, get the v by itself. That's v? Thank you. I guess it's going to be v equals the square root of 2 times 166.6 divided by 42. Or is it? I can't do physics with grams either. 42 grams, how many kilograms? It's 0.042, it's divided by 1,000. which is what? $7,000. That's square root, Mr. Duke, square root. And I get 89.1. Does that seem right? You know what? I've seen arrows fired. 89.1. That's about the length of a football field in about 1 second. That's fast enough that you can follow with your eyes, but still really fast. That seems ballpark about right, because arrows aren't like bullets. I can follow them with my eyes, where a bullet I can't. So they don't go that fast, but they're going to go a lot faster than someone just throwing something. Yes? So I'm good with that. That seems about right. My Nerf dart gun works very similarly. I apply a force over a distance. I've now stored energy. What kind of energy will it get transferred into? Kinetic. Okay. It's actually not very efficient. I've actually taken a scale and measured the force and measured the distance and calculated how much energy is stored in here. And then I've put that on a scale. And just like we did here, I've calculated the theoretical speed that this should leave at. It should be leaving scarily fast. So they must have a lot of governors in here, or they must bleed off some of it. Although it probably suggests you could take this apart and override some of the safety mechanisms. I think Adam Savage did that once for a Nerf dart gun and got it going pretty fast. Example 4. A model plane flies horizontally at 22 meters per second. Okay. A, calculates kinetic energy. Kinetic energy is going to be a half mv squared. Oh, straight plug and chug. Sheesh, Duick. This must be physics 11. .22 squared, that's going to be 121 times 4, so that's going to be 484. Half of 400, is it 484? Double check me. I think I'm right. Yeah. Joules. Let's suppose the model plane goes into a power dive and levels off 40.5 meters closer to the Earth. How much potential energy did it lose during the dive? Well, I think that's going to be gravitational potential energy. I think it's going to be mgh. It's going to be 2 times 9.8 times 40.5. Oh, that one I can't do in my head. I get 793.8. If you called it negative because it's an energy loss, I'd be okay with that. Or you're just saying that's how much it lost, that implies a negative. So I wouldn't be fussy whether you put a negative or positive there. How much kinetic energy did the plane gain during the dive? 738. So 793.8, because that energy's got to go somewhere, Hannah. It went into making the plane speed up. And again, this may be Captain Obvious, but that's why planes speed up when they dive down, and that's why when they go up, they slow down. The energy's got to come from somewhere. That's why you speed up when you ride down a hill on your bike, and that's why when you try and coast up the hill, you slow down. You're losing energy, you're losing kinetic, because you're gaining potential. The energy's got to come from somewhere. What's its new kinetic energy? I guess kinetic energy final is 793.8 plus 484. You can see I'm walking this max through many steps the way I would have done in Physics 11. In Physics 12, I would have no problem just asking part E, telling you how fast it's going, how much it died by, how fast are we going now? Get there, please. I get 1277.8 or 1,280 joules if I go to 3 sig figs. And E wants me to find its new horizontal, should say speed, not velocity. I'll have to remember to change that because we're in Scalarville. How would I get the V by itself in the kinetic energy equation? And I get, first of all, faster. That was my built-in error check. I knew the answer was going to be bigger than the original 22 meters per second. I get 35.7. meters per second. Roller coasters, finally. Roller coasters. I like this question. I like this question. I like this question. I'll just say it. You're absolutely going to see a roller coaster or 5 on your test. How would I know? It's roller coasters. Suppose a roller coaster's at rest. Oh, that's very nice. At the top of the first hill, it's given a very gentle push and it starts to roll. How fast will it be going at location A? Camille, what's this question asking me to find? Okay, so a V. Did it say velocity or did it just say how fast? Is there a change in height? Is there a change in height? Is there a change in speed? Is there a yucky curvy path? Conservation of energy. So Ke initial plus Pe initial equals Ke final plus Pe final. Did this question want me to include heat and friction? Nope. Hey folks, are any of these 0? I guess we're starting at rest. Technically not, because they're given a very gentle push, but let's say it's so gentle that it's technically 0. Okay? Sorry? Or we're ending up on the ground? Cool. So we're going to get mgh initial equals a half mv final square. Oh! Huh. What do you notice? What cancels? Camille, have you been on a roller coaster before? Before you got on the roller coaster, did they make you stand on a scale? Did they have to spread out heavy people and light people? Would an empty coaster car make it through the track the same way as the full coaster car would? Why? Camille, what are we trying to find? Let's get the V by itself. V is going to be, 2 Ke. Sorry. V is going to be 2 GHI. I was doing that wonky. Or is it? Square root. Two times 9.8 times 90. This might work out even, or to a nice number at least. What do you get? $42 even? Multiply that by 3.6. How fast are we going? In kilometers per hour. Sorry? I'm going on this. This is a good coaster. I've been faster, but this would, yeah, I'm going on this. Okay. B. How fast will it be going at location B? Good question. We're going to pick up with this on Monday. Questions you can already do. You can try number 1. Okay? Take a look at number 1 from the homework, because number 1 is so easy that it's tough. Here's what I mean. First of all, ME, mechanical energy, is just potential plus kinetic. What's the person's energy? What's the person's potential energy here in location 1? Be obvious. How much potential energy do they have here? 0. They're on the ground. Did they give you the mass? Yes. Did they give you V? Sorry. Yes. Could you calculate the kinetic energy? So you got the total energy as well. The total energy stays the same all the way through. From that, you should be able to figure out what's missing. Okay, so you can try number 1. You can try number 2. A little roller coaster. If you want to, you can try number 3. Eventually, I'm going to be assigning all of these, but if you're wanting kind of a head start, you can try those. We'll continue with this on Monday. More physics toys on Monday. Oh, yes.